Yes. Fine, sir. Thank you, sir.
Yes, that's fine.
We will start the session. Good afternoon to all. IEEE Power and Energy Society, NIT Calicut Student Branch Chapter in association with Industrial Power Group and IEEE Power and Energy Society, Young Professionals Kerala welcomes you to the International Lecture on Electric Vehicle Fast Charging Station, Prospects and Challenges. Today, we have two speakers for the session. Firstly, I would like to welcome Professor Mohan Kolhe, Faculty of Engineering and Science, University of Agder, Norway. Professor Mohan Kolhe has more than 25 years academic experience at the international level in electrical and renewable energy systems. He is a leading renewable energy technologist and has previously held academic positions at world's prestigious universities. He was also a member of the government of South Australia's Renewable Energy Board and worked on developing renewable energy policies. He was also leading the EU FP7 Smart Grid ICT project, Scalable Energy Management Infrastructure for Household, as technical manager. He has been successful in winning competitive research funding from the prestigious Research Council for his work on sustainable energy systems. He has published extensively in energy systems engineering. Next, I would like to welcome Engineer Sandun Konara, Faculty of Engineering and Science, University of Agder, Norway. Engineer Sandun Konara has teaching experience as a Faculty of Engineering and Science at University of Agder, University of Rohana. He has also been a visiting lecturer to Gale Advanced Technological Institute. He is consistently active in doing research in the areas of power electronics, electric machines, electrical motor drives, power systems, renewable energy systems, control systems, embedded systems, and mechatronics. He has published several research articles in different areas of electrical and power engineering. He worked as a research assistant in the SEMIA EU FP7 research project at UAE, Norway, along with Professor Mohan Kolhe. He won the Best Master's Thesis Award in Renewable Energy at UAE in 2016. We welcome you, sir. Next, I would like to extend my welcome to all the participants attending the session. If you have any queries, kindly put it in the chat box. That can be taken towards the end of the session. Over to you, sir.
Yeah, Atul, yeah. So can you see the screen now?
Perfect, sir.
Very good. So I'm very much thankful, especially to NIT Calicut and IEEE PS Kerala chapter for organizing this lecture on electrical vehicle fast charging stations. What are the prospects and challenges? At the University of Agder, we are working on different aspects of the electric vehicle technologies. Before going into the lecture, I would like to give you brief background about my research work. So at this moment, I have 6 PhD students and they are working mainly on smart electrical energy system. For example, Konara, he is working on how we have to do the charging coordination of electric vehicles at the fast charging station. This is a very unique work. Then another student in cooperation of FHV Austria, she is working on impact of electric vehicles within the distributed network, considering the home charging units. Then one more PhD student, he is working on using machine learning approaches or the techniques for demand forecasting and how that demand forecasting can be utilized for the grid operation and planning also. Then another student who is working on how we have to find out the photovoltaic hosting capacity within the distributed network at different nodes, and that PhD is also in cooperation with FHV Austria, or maybe we can Fachhochschule Applied Sciences University in Austria. Then another PhD student, that PhD is sponsored or supported by industry, Rema 1000, which is a very big supermarket chain here. So he is working on developing, right, energy management strategy for reducing the peak demand and at the same time utilizing the shifting of selected loads such as thermal inertial loads, and for that then he is using some artificial intelligence based techniques using the black box approach for managing this, that complete warehouse in an intelligent way so that it can reduce the peak demand on the network and can utilize the locally produced renewable energy and the energy storage. So now we will move to the second slide. Good. So today we would like to talk with you, or to give the high level overview, why we need the fast charging stations for the electric vehicles. So this work is related to the PhD work of Sandun Konara, and already Atul has given good introduction about Konara. Konara is working on this topic from last 3 years, let's say 2.5 years, and his focus is that especially when we have the fast charging station, how we can coordinate electric vehicles considering the different category of the users. So we are working on that one, and very soon some research articles, those research articles will be available in the public domain also. So as we know that the electric vehicles, the capacity of the electric vehicles are changing very fast due to the rapid development into the battery technology, as well as there is a strong demand in that for all countries to reduce the greenhouse gas emission. For reduction into the greenhouse gas emission, we have to move towards the sustainable transport. And when we are talking about the sustainable transport, then we have to move towards the electric vehicles or e-mobility. And at some point, many car manufacturers, they are also trying to move on hydrogen-based vehicles also. So at this moment, if we take into account the present situation, it seems that electric vehicles are going to dominate into the transport sector for next 20-30 years. So if we take the Norwegian case here into account, so on the road, out of 10 vehicles, around 6 vehicles or 7 vehicles, they are the electric now. Okay, and these electric vehicles, they are having very different capacity depending on the users, what type of range they want, what type of financial capacity they have. So here, I mean, the trend is that now most of the time, the people, those who are going for the long distance, they are moving or they are buying the electric vehicles, which has a very higher range of more than 300 kilometers in one charge. And those who are targeting to be in the city, right, or within the urban environment, so they are having the electric vehicle range of around 200 kilometers. So considering all these points into account, Konara developed his research proposal or his research objectives in his PhD work, that if this trend is going to is happening now, right, how this trend is going to impact, right, in developing the fast charging station, not only developing the fast charging station, but what the operational challenges are going to be there, and how these operational challenges can be solved by considering the different categories of the users. For example, primary user or secondary user, or or maybe we can define in a different way also. Because earlier or few months before, the electrical energy price in Norway was very low. But in the last 1 month, due to internationalization or due to the international market, the electrical energy price have been increased dramatically. Earlier, we used to pay the price maybe a 0.5 cent per unit of energy, something like that. So now it is gone, maybe let's say €5 per unit. So it is a drastic change, right? So it may also impact the operation of electric vehicles also. So most of the users, they are trying to charge their electric vehicles not at the home, but they want to utilize the facility available at the fast charging station. So here you can see that if we have to promote the electric vehicles, for the promotion of electric vehicles, we need to have the fast charging station. So this approach has been taken into account in Konara's research work. Before joining the PhD, Konara did the master thesis here, and in his master thesis, he developed very unique algorithm on how we can have the controllable dispatchable power with integration of photovoltaic and energy storage as an active generator. So that approach also we are going to integrate into this fast charging station. But he is putting more focus at this moment on operational management. So that was just like a overview, high level overview of today's lecture. And in today's lecture, we would like to give you more emphasis or at high level so that you can generate your interest in doing further research work or maybe research work in cooperation with the industry or field oriented work related to the operation of electric vehicle charging management system. We are not going in much detail but we want to have the information at the high level. So first, I have just given you some background. Then I'm going to give you the motivation also. Then international standards for EV charging stations. What type of architecture for fast charging stations should be there. Fast charging station deployment analysis. How the operation mechanism management can be done. And then we are going to provide you high level conclusion from this lecture. So in this slide, you can see that this work or these pictures have been taken from International Energy Agency. If we take the simple scenario that is called steps, without giving any acceleration, by 2013, it is expected that around, let's say, 150 million electric vehicles will be there into the market. Most of these electric vehicles are going to be into the category of passenger battery electric vehicles. Then some category, it will be the plug-in hybrid electric vehicles also. And then of course, commercial electric vehicles and buses, purely battery and maybe plug-in hybrid also. But if we consider the accelerated scenario, and this accelerated scenario has considered that in most of the countries, they are targeting to have the zero or net zero target. So to achieve the net zero target, most of the countries, they are saying that by 2050, we will be net zero, and India has agreed by 2070, that will be the net zero. So to become the net zero, of course, we have to focus on sustainable transport. And within the sustainable transport, electric mobility is going to be the main part. So if we consider that scenario into account, so as per international energy statistics, by 2030, you can see that around 250 million vehicles will be there based on electrical energy system, right? And again, there also you can see that the passenger vehicles or the normal electric cars, what we can say that they are going to be dominating there. So when we are going to have this scenario in reducing the greenhouse gas emission, and at the same time we want to achieve the net zero target, then you can see that how the electrical energy demand is going to increase. If we take the simple scenario situation as it is, then by 2030, you can see that around 500 TWh electrical energy is going to be required. And if we take the accelerated scenario, then let's say it is going to have the requirement of around 1000 gigawatt hour energy. And most of these are going to be into the category of light duty vehicles, where most of these passenger electric vehicles will be there. So if we take into account this, so in the next slide, you can see that how the different architecture of the electric vehicle propulsion system is going to be there. The first one is the simple, that is the international combustion engine, right, where we are feeling. But the second one is very interesting, that is the battery electric vehicles, and the third one is plug-in hybrid electric vehicles. So if we take into account the previous slide, then most of the contribution are going to come from battery operated electric vehicles or plug-in hybrid electric vehicles. Okay, and then some of the car manufacturer, they are also focusing on fuel cell based electric vehicles. We will briefly cover that also. So but most of the focus, right, from fast charging station development point of view is going to fulfill the requirement of battery electric vehicles and plug-in hybrid electric vehicles. Now here, and this table have been taken from IEEE, or it is widely available. So here you can see that the commercial electric vehicles which are available into the market, so they are having their capacity, let's say, from a different range. If we take the, let's say BMW i3, it is having the capacity of 137 kilowatt. And if we go to the Tesla Model 3, it is having the 635 kilowatt, okay, which is very high. So here you can see that there is a wide range of capacity of the electric vehicles which are available into the market. Here, I would like to highlight that because all these vehicles, they are available into the market. And I had the opportunity during the summer holidays to do the test drive of all of these vehicles. So while doing the test drive of all these electric vehicles, I observed that each of the electric vehicles is operating in a very different way, and the software or for the electric vehicle users, they are also very different, right? Some of the cars, they have this display software more or like a conventional car. And for example, but if you take the Tesla or especially Model X or maybe Model Y or Model 3, so their software or the user display is very different. And when I was driving the Model 3, so in the Model 3, you can see that how the adaptive cruise have been there, how the 360-degree camera, they are sensing all the objects together. Based on that, all the speed and all the functionality of the car, they have been activated and like that. So here, what I want to say that every car has a different type of architecture, different type of software, different type of control functionality. So for most of the time for the users, right, we are not going to touch any software or any functionality of the car, right? And it is not allowed to open a single screw of any car, otherwise you are going to lose the warranty. Only thing is that we have to charge the car. So then the question comes like how we have to do the charging management, especially from the supply side point of view. Okay, so here you can see that all these electric vehicles, they are having different range of the battery voltages. But here you can see that most of the battery voltages are between, let's say, 350 to 400 volt and something like that. But there is a one vehicle Porsche, it is going to require the voltage of 800 volt. So at this moment, most of the charging station, they are utilizing the voltage level at 400 volt. And here you can see that depending on their battery capacity, different type of kilometer range they have been described here. So let's say if we consider the Tesla, then it is having the very high range, and it is, of course, then it is going to have the higher capacity of the battery also. So then when we want to charge this battery capacity, if we use the normal home charging unit, so it may take overnight to get it charged. But when we are driving, right, we have to utilize the fast charging station to get the juice in our battery within a shorter period of time. So how we can achieve that? That is going to be the key objective for that. So here the motivation for the fast charging station is that if we consider, let's say, 2030 scenario, 40% of the total energy demand is going to come for the fast charging station, and even it is going to increase. Similarly, if we consider the figure 5, so in the figure 5, like as the number of electric vehicles are going to be increased, and when we want to have the more distance in one charge, then naturally number of daily fast charging events are going to be increased. So when we are having more number of daily fast charging events, that can be provided through the fast charging stations. So here from the supply side or from the operation side or from the, let's say, from the user point of view, or to make the user more satisfied, we need to work on fast charging station. So that is the main thing here. So let's say if we want to have the fast charging station here, so here you can see that the fast charging units, that is a number 6 in figure number 6, right? So it is going to provide the supply to the battery of the electric vehicles, and of course then that supply is going to be used in powertrain stage. The question is made like at the point 6, right? Because we cannot do anything within the electric vehicles. That is going to come as a black box. We are not even allowed to change a single screw, otherwise we are going to lose the warranty of the car. So now here from the supply point of view or from the operation point of view, right, and to reduce the demand within the distributed network, we have to work at the point number 6, that is the fast charging station. And the fast charging station has to get some information from the car that is going to be provided through the cable number 3, as well as that information from the unit number 6 has to be communicated to the fast charging station operator also. So for that point, we need to utilize so well established international standards, for example, IEEE 61851 as well as IEEE 62196 also. So here you can see that so these standards, they have been used by different charging units. They have been classified. I'm going to take those classification into the next slide. And then these standards for the EV charging station, again, they depends on region to region also, and how those points can be, or those units can be used. Let's say if we take the standard CHAdeMO, right, it can go up to the maximum voltage of 1000 volt, and it can be up to 400 kilowatt. Okay, and it has the communication based on the CAN. Then GB/T, CHAdeMO is used in the Japan, and GBT is used in China, and CCS type 1 mainly in Europe, CCS type 2 mainly in North America, and Tesla, they have their own dedicated charger or specification or the standards, I can say. Then another which has been going to be developed, especially taking into account Japanese CHAdeMO and Chinese GBT, which is going to work at very high voltage level of around 800 volt, and it is going to help in fast charging station also. So here you can see that only this CHAdeMO is going to have the functionality from vehicle to grid, but remaining are not. So here this is another very interesting point. What I have seen in many IEEE articles, so many academicians, they are working on the point of view from vehicle to grid. But here we believe that when we are talking about the fast charging station and getting the electric vehicles charged at the fast charging station, so then this vehicle to grid functionality may not work or will not be useful at the fast charging station. That may be useful at the home level charging station. But another question point is that most of the car manufacturer, they are not allowing to have this bidirectional, except for example Nissan, they are doing some demonstration into the Denmark and UK, that how that functionality of vehicle to grid is going to work, right? So let's say we will forget about the vehicle to grid point. Our target is that how we can provide the electrical power, or how we can get the fast charging to the electric vehicles in the minimum time. So for that minimum time period, right, how we have to do some coordinated charging at the electric vehicle stations. That is going to be very important, because we know that at a fast charging station there may be n number of plugging points, and at n number of plugging points, n number of electric vehicles, they might be connected. Some of the electric vehicles, they may be in a position to pay higher because they want to get it charged fast. Some of the electric vehicle users, they may want to pay less and they want to get the less charge also. So all these things we have to coordinate it in a systematic way, and accordingly we have to do we have to develop the fast charging station, and then we have to develop a software or a control system for optimizing or coordinating the electric vehicle charging in a distributed manner. So here in this slide you can see that our focus is now on the fast charging station, and here you can see that, let's say if we take the case of the Tesla Model 3, it has the capacity of 72.5 kilowatt hour, and it has a range of 450 kilowatt, and required charging power is 174 kilowatt, and actual maximum charging power is 250. This 174 kilowatt is going to be required if we consider this vehicle has to be charged within the 15 minutes. So here you can see that how much demand it is going to be there. So how we are going to manage that demand in a coordinated way. So if the electric vehicle which want to get it charged on the drive, on the highways, or in the public road network within the 15 minutes, so how that demand has to be managed. So for example, if we take the BMW i3, which is having very small capacity, and its driving range is of around 235 kilometer, so it has a battery capacity of 37.9, and if we want to charge this BMW i3, which is a very small car, as per the compared to the Tesla. So during the 15 minutes, the 91 kilowatt power is going to be required. Okay, that 91 kilowatt power is again taking into account the charging from 20% battery state of charge to 80% state of charge, right? But at this moment, the maximum actual charging power for BMW i3 is only 49 kilowatt. So we have to consider all these points while making the planning of the fast charging station. So now here, when we are talking about the fast charging station, so there can be different type of architecture. So let's say if you consider the figure 6a, so in the figure 6a, so considering the distribution transformer, right? So there may be different units, right? And of course we need to have centralized storage also, so that we should be in a position to fulfill the fast charging demand within the limited time, considering the grid constants. But now, due to the advancement in technology, this distribution transformer can be replaced by the solid state transformer, or maybe using back-to-back converter and reducing the peak demand or reducing the active power demand by a certain amount from the grid and getting it fulfilled from the local energy sources or the distributed energy sources, including energy storage. So here, one point is very important, that in Konara's master thesis work, he developed one architecture where energy storage, solar photovoltaic, they have been integrated together, and that integration was based on AC microgrid architecture, where we implemented the Droop functionality to provide the instantaneous power, okay, for the local loads. So such type of scenarios can be further modified. In place of AC microgrid architecture, we can use the DC microgrid architecture for fulfilling the load which have been described in figure 6b. Then if we go to the figure 7b, then figure 7b is basically the extension of figure 6b. But in figure 7b, there is another local storage at different units also, and the centralized storage also. And then here centralized storage, we can say that maybe integrated with the renewables also, or maybe local distributed generators, and doing the communication and the control with reference to the local units, we can manage the power flow at each charging point in a very distributed way, so that charging management can be integrated in a very systematic way, where we call it, let's say, aggregated way or maybe adopting way, where we can fulfill the charging demand of electric vehicles depending on which type of electric vehicle is there. For example, if it is a BMW i3, then the requirement is going to be different. If we take the Tesla Model 3, then it is going to be different. So for that, we need to have the charging coordination strategy, where we want to have more research focus, and that research focus we are considering in our in the PhD work of Konara. Then another here, the architecture of fast charging station. So here the first figure 8a is basically correlated to the figure 6b figure 6a, and figure 8b is more or less correlated to the figure 6b in the previous slide. So here you can see that we need to consider different power conditioning devices topology, right, in which we should be in a position to do the charging management of electric vehicles. Then another very interesting topology, it may come into the future, but we believe that it may take more time. Here, very interesting thing which have been mentioned about the using the hydrogen as an energy carrier, or maybe storing the electrical energy in the form of hydrogen also. So here you can see that we configured electrolyzer and the fuel cell. So electrolyzer is basically utilized for producing the electrolytic hydrogen when we have the excess energy and storing it at a particular pressure, and then utilizing it through the fuel cell for producing the required amount of electrical energy. And I did very good work on this integration of renewable energy sources, where we can store the electrical energy in the long term, form on electrolytic energy, electrolytic hydrogen also. So here figure 6b is basically the modification of figure A, where we tried to have the isolation through DC-DC converter so that the unit can operate autonomously or without getting impact on the backside also. So those were the, let's say, overview of the fast charging station. What is the market need is there, because we know that we cannot control, we have seen that the electric vehicle market penetration is increasing exponentially. Different type of electric vehicles are coming into market. So we have to adopt that, or we have to supply the different type of electric vehicles in a systematic way, reducing or in managing, right, charging demand locally, right, so that the existing distributed network can help us, right, to cope up with upcoming demand of electric vehicles, where the focus is on e-mobility. Then next slide. In this next slide, we have given the overview of fast charging station deployment and operation mechanism management. So here you can see that charging station control system is the main, where the fast charging station operator is going to be there. So at this fast charging station operator, let's say we have some electric vehicles. So these electric vehicles, depending on the different manufacturer and their different capacity and their requirement, it is going to make a charging demand to this fast charging station, right? And then of course, this fast charging station operator, it is going to have some limitation from the grid also, or distributed system operator also. So we need to consider that power system risk analysis. Then another very interesting thing is that we have to use the navigation control system or navigation platform, where the electric vehicles which are outside of the fast charging station, so they can communicate it through this navigation control system to this operator, right, of this fast charging station, and can make the virtual request also. Yes, if you have the available facility of this much, I can come and plug in my electric vehicles to get it charged. For that, we need to have the traffic network information also, some dedicated navigation platform also. So some of this functionality has already been incorporated into the Tesla software. So when we drive the Tesla, we can get all this information, how much charge is remaining there, and then also we get the information that in the neighborhood area where we have available Tesla charging station, because they are the dedicated one, right? So for the Tesla we cannot use any another one. And then based on that, we also get the information where the charging points are empty. So, but at this point, we are not getting in a position that how much power is available there, because at this time, the charging has been done at the constant rate, not on the aggregated based or the adaptive based. So now, from the research point of view and for the further implementation field implementation point of view, we think that in near future, this fast charging station operator, they have to provide the power supply to the electric vehicles in adaptive way or as per the requirement of the electric vehicles, not as at the constant level what it is going at this moment. So this slide is going to provide you overview of fast charging station deployment and how we can develop the operation mechanism for that. So this slide is very key for providing you further explanation of fast charging station, operational mechanism, coordination of electric vehicles, and so on and so forth. So now I will hand over to Konara so that he can explain you that how the fast charging station can be utilized for charging the electric vehicles of different categories at different power level in a coordinated way, considering the real operational or the electric vehicles which have been connected at the fast charging station, and as well as the electric vehicles which are in the virtual queue also. And this operational mechanism is going to help in making the profit to the fast charging station operator also, and also selling his available resources in a systematic way to the electric vehicle users also. So, Konara, please.
Okay, I'll take it. Okay, thank you, sir. Greetings from University of Agder. I believe, am I audible? I think, right?
Fine, sir. Audible.
Yeah. Okay. So I believe you got a very good insight, a very good understanding about the so-called physical layer, which I am used to say, because we should have very good understanding about the physical layer to move into the computational layer. So far, Professor Mohan very nicely described the state of art and the standards and the architectures of fast charging station. Actually, in this lecture, we are giving sort of high level overview, because if we consider a certain topic, we can talk days and days, because this is very interesting area. So in order to give you insight and some, if you want to find some new research directions, that is the main motive for us to give this lecture. Okay, as a summary, what Professor Mohan described so far, I have incorporated this slide. Here, as you all know, we are moving towards the sustainable goals through net zero emissions pathway. So in that respect, we always interested in clean solutions. Of course, electric vehicles can be considered as a clean solution as compared to the fuel-based vehicles. So, but when we are trying to move towards the electric vehicles, the current the current practice is charging electric vehicles with AC chargers. But when we are trying to charge our electric vehicles with AC chargers, we have some challenges. Actually, a long charging time and the range annexity, because we don't have any guarantee about the range with one charge. And most of the EV users do not have detached houses. Then charging autonomy issues come into the picture. So these are serious challenges in adaptation of electric vehicles. So with the rapid advancement of energy storage and conversion technologies, as a solution, DC fast charging is there. So in order to move towards DC fast charging, what we have to do is we have to think of widespread of charging stations. When we are trying to do so, that means when we try to rapidly deploy fast charging stations, then we are getting another challenges or serious negative impacts on the power grid. Okay, because if you try to transfer from fuel-based fuel-based transportation towards the electric transportation, so you are going to add high load to the network, and because of that the issues may come with network capacity and the power quality, and especially electricity market operation, so on and so forth. So then we should find some innovative operation mechanisms to cope with these challenges. Okay, in that respect, you should have very clear understanding about the physical layer and the standards and what are the limitations of the available technology, and what are the ongoing research related with this electric vehicle supply equipment, so on and so forth. We should have very good understanding about the physical layer, which was described by Professor Mohan so far. So actually, this is kind of a abstract to the Professor Mohan's lecture to move towards the computational layer from the physical layer. So here in this slide, I request from you to not much worry about these numbers, because here actually I have taken these two figures from one of my journal article. Actually here I want to emphasize the need of innovative operation mechanisms or charging coordination practices. Here, if you consider this blue curve, you can see that is the energy demand of the fast charging station if we left the charging process uncoordinated. That means it exerts a severe stress on the network. So by incorporating some innovative operation mechanism strategies in terms of charging coordination, what we can do is we can effectively reduce this stress to the network. Actually, you can see from the yellow curve and the maroon curve, you can see the different charging mechanisms. I mean the power profile resulted from different charging mechanisms, but I'm not going to go into detail. Here I want to give you insight, the importance of innovative operation mechanisms, operation management strategies. So therefore, what we have to understand at this point, when you are introducing a fast charging station, it should always come with innovative operation mechanism. Otherwise, so you will create another problems. But when you are trying to do so, in the figure 14, you can see the blocking probability of electric users is increasing. You can see in figure 14 a continuous ascent in the blocking probability with respect to mean arrival rate of electric vehicle users. These are the challenges. Then we should understand, when we are proposing innovative operation mechanism, the charging coordination strategies, we are getting another sort of challenges, especially related with quality of service. So therefore, we have to consider all these things in proposing innovative operation mechanism strategies. So then, when we come to this fast charging station deployment and the operation mechanism, I'm going to describe this topic in four subtopics. That is optimum sitting and size of the fast charging station, and the techno-economic sizing of the fast charging station, and the charging management or optimum scheduling of electric vehicles within the fast charging stations, and overall performance assessment of the fast charging station. So if you consider these main four areas, main four subtopics, we can summarize or we can abstract this whole process into these three main objectives. Actually, with this computational layer of a fast charging stations, what we are trying to achieve is basically we are trying to maximize the fast charging station profit. And then while maximizing the profit of the fast charging station, we need to minimize the impact to the power grid as well as the electricity market. And also, we need to provide at the same time, we need to provide high quality service to EV users as well. So basically, these are the main three objectives we need to achieve in deployment and proposing different operation mechanism strategies, and also deployment analysis. Okay, now I have step 2, fast charging station deployment analysis. So this is a very interesting area. Actually, if you consider a fast charging station, as you can see in this figure 15, you can see M number of, let's say, M number of electric vehicle supply equipments. But actually, behind this M number of electric vehicle supply equipments, there should be a dedicated energy source, maybe renewable energy system or energy storage or local distributed generator as described Professor Mohan in his part. Because fast charging station is not recommended to be depend on the grid or solely all the times because of the high demand of fast charging stations, high as well as rapidly changing demand. Therefore, there should be a supportive, dedicated local energy supply. In that respect, we have to find the optimum sitting and the size of the fast charging station, and also the optimum sizes of different components in fast charging station. Any question?
Participants are kindly requested to mute their mic.
Okay. Okay. So basically, if you refer the literature, you can find optimum sitting and sizing of the fast charging stations and the techno-economic analysis of different components in fast charging stations under fast charging station deployment analysis. Okay, so when we come to this optimum sitting and size, we'll move on with certain perspectives of finding the optimum site with the optimum size, of the fast charging station, along with typical techniques. Actually, this perspectives is very important to model this fast charging station deployment problem, then these aspects will be analyzed with different techniques. Okay, so if you consider figure 16, you can see actually fast charging station should not be installed only based on the availability of a land or a space. We have to perform comprehensive analysis about the possible traffic within the area within which your fast charging station going to be built. In figure 16, you can see in this particular analysis, they have considered different zone of that particular area, and within these zones, they model the possible electric vehicles. Not only within that area, they have considered the possible arrival to this zone from out of this particular area. That means out of this core, because it is very important to pay your attention the charging time of fast electric vehicle charging, because when you come to fast charging, it is not very long as compared to level 1 or level 2 slow charging, AC charging, but it is not very short as compared to refueling of fuel-based vehicle. It is in between. Typically, it is in between 10 minutes to 45 minutes, depending on different aspects of electric vehicle and the electric vehicle supply equipment. Therefore, you have to consider the traffic within that particular area and also the possible traffics that can arrive to that particular area. So by considering those information, we can find what is the optimum sitting of your fast charging station and what is the optimum number of electric vehicle supply points. So in this context, first we are going to consider the perspectives to find the optimum sitting and the size of the fast charging station. So in literature, you can see authors have considered construction cost aspects, because if you're going to construct fast charging stations in different zones, depending on the practical issues, the construction cost going to be different. Therefore, this is a very common aspect that authors have taken into account in proposing different fast charging station deployment strategies. And then the service quality aspects. As the service quality aspects, basically in literature, you can see the authors have considered waiting time at the charging station and the driving distance to the charging stations. Because if you consider your electric vehicle is in zone 1 and you are going to deploy your charging station zone 3, there is a certain distance in between zone 1 and zone 3. Therefore, authors have considered basically waiting time and the driving distance. But with my experience, this is an area where there is a research gap where we can incorporate some other aspects as well. That is also very important. And the grid stability, because if you consider the power grid, depending on the area, the strength of the power grid is different. Therefore, we have to consider the grid stability aspects in proposing different fast charging stations deployment strategies. So these aspects can be modeled with these techniques. Now I'm going to explain these different techniques. So basically, mainly we can see optimization models and graph theory based models and queen theory based models. Of course, I need to highlight that the techniques are not going to be limited to these three. Depending on the nature of your problem, you can incorporate whatever your convenient technique, but if you refer the literature, you can see these are very common and very typical techniques with which these aspects are modeled and analyzed. Here, I want to highlight one important point, that is, when we are proposing a deployment strategy with the objective of, let's say, construction cost aspects, the other aspects can be taken as constraints to that particular problem. Therefore, these aspects can be used as objectives as well as the constraints in formulating your fast charging station deployment problem. Actually, as Professor Mohan explained, fast charging station, it is not recommended to come up with only grid supply. It should be supported by a renewable energy system or an energy storage or local distributed generator. Therefore, we need to properly size all these components. Therefore, the analysis associated with this sizing comes under techno-economic sizing. This is also a very interesting area where you can work. And that is the fast charging station deployment analysis. Now I'll step to the operation mechanism management, because once you deploy a fast charging station, definitely we'll have to focus on innovative operation mechanisms. Otherwise, you will not be able to effectively, optimally utilize your charging resources. Of course, which includes electric vehicle supply equipments and the local distributed generators, renewable energy systems, or energy storage. Then you should have innovative operation mechanisms. Otherwise, you will lose your potential customers because of the service dissatisfaction due to high blockage and high waiting time, high charging time, and those things. So in this context, first I would like to talk about charging management or optimum scheduling. Actually, here I will give you an overview for charging management. This is not focusing on a fast charging station. This includes residential charging as well. For a certain area, if you consider a certain number of electric vehicles, in the centralized EV coordination architecture, all the electric vehicles are coordinated by a central aggregator. But the thing is, here you will be getting issues in terms of computational complexity and the scalability when your number of electric vehicles is going to be increased. Therefore, researchers were moved towards decentralized electric vehicle charging architecture, in which this computation, the relevant computations are distributed to the end users or to aggregators. Actually, when we come to electric vehicle charging stations generally, because fast charging station is also a subset of electric vehicle charging station. So this is the very common architecture. This is known as distributed hierarchical architecture. That means we can propose our control strategies in this way, in this hierarchical manner. The importance of this hierarchical architecture is we can distribute our complete charging management problem into different stratas, different hierarchies. By doing so, we can address many aspects associated with charging management. So, as you can see here, the electric vehicle initially aggregate to the charging station at the lower level, at the lower layer, and the charging station controller will report this aggregated information to the immediate upper layer for computations. Then the aggregator, who is placed in the second layer, can incorporate with the aggregators of upper layers to perform this charging management or optimum scheduling. Actually, I want to highlight this number of layers should not be limited to 2. You can have as many layers as you want with the cost of computational complexity. It is not recommended to have more than 3 layers. In most of the cases in literature, we have seen maximally authors have used up to 3 layers. So here we'll try to move on with different aspects associated with charging management and optimum scheduling. It is control aspects and the timing aspects, and these aspects are modeled with these techniques, different techniques. We are going to basically consider in this slide different aspects on which these charging management and optimum scheduling problems are formulated, and then we are going to look at how these aspects are modeled and analyzed with typical techniques. This is just overview, because if you consider one particular strategy, we can talk hours and hours. So here I have used one architecture that I have used in one of my paper. Actually, this is a practical application or practical implementation of a hierarchical approach of coordinated EV charging, which I explained in the previous slides with the figure number 19. Here you can see electric vehicles will be aggregated at the lower layer, and the energy controller at the lower layer will report this information to the immediate upper layer. And then at the immediate upper layer, it is charging station aggregator. Actually, in this particular work, charging station aggregator owns several charging stations within certain area. That means between the charging station aggregator and the charging stations, you have a direct connections, because in some cases, of course, it is not necessary to have direct connections between the aggregator and the charging stations. You can have virtual connections as well, as you saw in figure 19. In this particular work, this the second charging station aggregator incorporated with the spot market and also the utility and also power grid in order to get relevant information, and based on that it performs the charging management. Okay, so Actually, a little bit stand up because otherwise I'm fed up. Okay, so I'm also bored. If you consider control aspects, okay, first I would like to step to the control aspects. Basically, they have considered as the control aspects the economic aspects, that mean maximizing the EV aggregator profit and also minimizing the EV charging cost. And then operation aspect, as the operation aspect, authors have considered several aspects. Optimum utilization of limited charging resources and different user preferences, because users have different preferences, because there is a vast variety of preferences when you come to user preferences, that is the plug-in time and plug-out time, waiting time, day-to-day frequency of electric vehicle charging, and so on and so forth, and the service quality. So the quality of service associated with your EV charging, and then grid stability. So those aspects very commonly have taken into account in proposing charging management strategies depending on your problem. So then I'm going to step to timing aspects. Timing aspects mean basically, as you can see in this picture, we have offline strategies and also online strategies. In offline strategies, what we are going to do is we are going to schedule electric vehicle charging process in advance time. So in the figure 21, you can see with green color, we have scheduled electric vehicles in, let's say, a day ahead by considering forecasted information. But when we come to real-time strategies or online strategies, we have to focus on, we have to remember that electric vehicles arrive to the fast charging station opportunistically. So then, depending on the real-time situation, real-time information, we have to perform the charging management. And but there are certain uncertainties associated with the fast charging management. When you come to offline strategies, we don't have a very bigger room where we can address these uncertain aspects, because since we are scheduling our electric vehicle charging schedule in advance time based on the forecast demand, we may not come across with a real mobility data and the demand uncertainties and the price uncertainties, and especially supply equipment failures, so on and so forth. There are several uncertainties are associated with electric vehicle charging management, but in offline strategies, it is very difficult to associated with, it's very difficult to cope with these uncertain aspects. But when you come to online strategies, of course, we can address somehow this uncertain aspect. But the thing is, we don't have much flexibility to shift the electric vehicle demand, the requested demand, in a certain time horizon. But in offline strategies, we have a room to shift the requested demand within a certain horizon. So as you can see in my last figure, the figure number 21, I have explained that actually basically in my PhD, my approach is how these uncertainties are addressed with different electric vehicle categories. And then I'm going to move to the typical techniques by which these aspects are addressed. Most commonly, optimization models we can find in the literature. So as typical optimization techniques, linear and quadratic programming and the stochastic programming, where we can address certain uncertainties, and convex optimization, because here we have to very clearly understand in online strategies we have to pay our attention for the computational complexity, because we are performing all these strategies in real time. If your proposed algorithm take lot of computational time, it is not a feasible or a practical solution. Therefore, we have to linearize, or we have to simplify your nonlinear problem, maybe with convex optimizations. And game theory and genetic algorithm, of course, not limited to only these presented techniques. There are some other techniques as well, but I have selected some typical, most commonly used techniques for your information. And some heuristic algorithms, because we can propose our own algorithm, our own pricing mechanisms, our own energy management mechanisms with heuristic algorithms, because rather going for available optimization techniques, we can propose some our own strategies with different heuristic algorithms as well. And also Q-based models can be incorporated to model these different aspects. Just like in the fast charging station deployment analysis, here also you can use one aspect as your main objective, and the remaining aspects, or several aspects, can be considered as your constraints. And there is another beauty with this hierarchical architecture, that is, in different stratas you can address different aspects. That is also one beauty associated with this hierarchical architecture. Because one of my paper, we have incorporated the demand limit, which is calculated at the charging station aggregator layer with what's called grid stability aspects, and this demand limit will be a constraint for the charging management problem at the lower layer, which is proposed as a heuristic algorithm. That in that manner we can incorporate several aspects in several layers in this hierarchical architecture. So then for this charging management problem, typically we are feeding energy price, power and energy, EV mobility, utility constraints, grid constraints, battery constraints. Of course, you have to pay a very intense attention towards these battery constraints, because you have very clearly identified with Professor Mohan's part, electric vehicle manufacturers manufacture the electric vehicles with different ratings, and we have to cope all these battery constraints in proposing feasible and practical charging management strategies. That's why actually we decide to put some slides on the physical layer, which I always prefer to say physical layer, because without a proper understanding of the physical layer, it is very difficult to propose feasible and practical operation mechanism strategies in computational layers of a fast charging station. And then the next part of the operation mechanism, that is very important, the overall performance assessment. Because if you consider a fast charging station, it is if you consider a fast charging station, there are some traffic inflows and traffic outflows. But the thing is, all the inflows will not be guaranteed plug into or admitted to the fast charging station. Some portion will be blocked. And also, out of the plugged in electric vehicles, there is no guarantee that all the electric vehicles will reach to the requested state of charge. Some portion could be subject to forced terminations due to several uncertainties. Therefore, we should have overall picture of this proposed strategies. That is very important. This is a very good area for you to work, because I have seen a serious research gap within this area related with performance assessment of different charging management strategies. In this analysis, what we are doing is we have to consider, actually it is just like looking the fast charging stations from the top. So we should see how electric vehicles reach to the fast charging stations, and what is the portion of electric vehicles will be connected to the fast charging stations, and what is the portion will be blocked from the charging stations, and how about the traffic outflows, how much electric vehicles will complete their charging process, and what is the percentage of electric vehicles which are already plugged to the fast charging stations will be subject to forced terminations. And we should have this overall understanding. So for that, you can incorporate continuous time Markov chain, discrete time Markov chain, and the Markov decision process, or reinforcement learning based models, so on and so forth. Different analysis you can incorporate to analysis all these blockages and the completions, utilization, and all these things associated with this overall performance assessment. As a conclusion, initially we have given you an insight to the physical layer. Always I'm using the word physical layer, where all the physical implementations are taken place, the current status and the relevant international standards. That is also very important in proposing feasible and practical charging management strategies, and what is the possible architectures of fast charging station. As Professor Mohan mentioned, we can build basically fast charging station as either AC microgrid or DC microgrid. When we come to AC microgrid, again, we have two options: AC coupled architecture and the DC coupled architecture, something like that. So there are certain architectures with certain distributed generators or renewable energy systems or energy storage with different control strategies. And also we have to find the optimal sitting of the fast charging station within a certain area. Before deploying a fast charging station, we have to analyze what is the optimum location where we can deploy the fast charging station, and what is the optimum number of electric vehicle supply equipment that can give the service to the electric vehicles right to the fast charging stations. Because fast charging station with this CHAdeMO standards, they are going towards the 900 kilowatt charging. It is not available in the market, but the research are going on. Therefore, very recently we are reaching the same sense that we get with the refueling of fuel. Any question?
Participants, kindly mute your mic.
Okay, so then it is one very important area where we can perform computational related analysis. And then once you deploy your fast charging stations with optimum number of electric vehicle supply equipment and the distributed generators or energy storage, then you have to pay your attention how you can effectively utilize these charging resources in order to earn maximum profit without disturbing or without exerting unnecessary stress to the grid, while giving quality service to your customers. And in that respect, I have highlighted, related with this overall performance assessment, there is a huge research gap where you can pay your attention as well. So thank you very much for your attention. Over to you, sir.
Thank
So
you.
these are the references. Thank you very much. And I hope you enjoyed the overview of fast charging station, and especially how we have to do the coordination of electric vehicles. In one of the slide, Konara mentioned that we want to do the coordinated electric vehicle charging, considering the different category of users. And as we know that there is some time limit is there for charging one electric vehicle. So of course, we are going to have some blocking probability also, or blocking of the electric vehicles for the charging. And maybe for the secondary users who are not prepared, or the primary users, they may have to force their termination of electric vehicle charging also. So this is a very interesting work, and we are trying to develop one algorithm in which we can have the coordinated electric vehicle charging at a fast charging station, where we can serve the primary users and the secondary user, and accordingly then we can manage the charging considering the available resources also. And such type of operational mechanism may be useful for the charging station operator to make the profit also, and also to establish and develop local distributed energy resources based on the demand which is going to be created due to the exponential growth of the electric vehicles, and with different sectors or the different capacities also. So now I request participants, if they have any questions, we will be very happy to answer their queries. And in the chat box, I have seen that one of the student or one of the participants, he has asked about vehicle to grid functionality also. But here we are talking about the fast charging station. In the fast charging station, this vehicle to grid functionality will not be there because we want to charge the electric vehicles as fast as we can. This vehicle to grid may work when we are using the slow charging and especially at the home also. Then again, it depends on what type of functionality the electric vehicle is going to provide, because at this moment most of the electric vehicles, they are just using only to or using the topology to charge the battery, not to discharge the batteries through the connection point to the other loads, right? So all these points we need to consider.
Sir, Professor, this is Dr. Sharmila from Anna University. Like how to get these real-time data? So because like how many vehicles are coming if you need, like in India,
Yes, correct. Yeah, so last night we thought to include that slide also, but we removed that slide. So there is a lot of data is available based on that how driving cycle patterns. Okay, based on the driving cycle patterns, users are charging or fueling their vehicles also. Then we have to see, let's say, if we consider the same pattern as the conventional vehicles for charging the electric vehicles, considering the same driving cycle patterns, so we may get that scenario also. And as we know that, I mean, depending on the country to country, the situation may change, right? For example, if we take the scenario of Norway, here we have around 60 to 70% electric, 60 to 70% cars are electrics now. So we know that there is going to be a lot of rush for the charging of the electric vehicles. And very few people, they are charging their electric vehicles at home due to the high energy cost. Okay, so to charge at the fast charging station is more economical compared to charge the electric vehicle at home. So all these points will help us in developing some scenario, right? How the charging patterns are going to be there. So that is also a good work. In our work, we used probability distribution functions of arrival of the electric vehicles also. So that probability function then, here we have used, let's say, continuous Markov chain method. We can use the Monte Carlo also, or any other well-established probability technique also for defining like what arrival of the electric vehicles are going to be there. And of course, then we need to have the data, but at this moment we may not have that data available as compared to the conventional cars, right? So we have to use that data, and then we have to make it like what type of capacity, what type of driving cycles are there, and so on and so forth. So we need to make some assumptions on that also. Isn't it correct?
Yeah. We can use the synthesized data related with electric vehicle charging, electric vehicle arrival at the fast charging station. That means we can incorporate stochastic programming to model the electric vehicle mobility process with different probability distribution functions. Okay, so then with that synthesized data, we can move forward.
Yes, Professor. Thank you, Professor.
Okay, thank you, sir.
Professor, this video could be shared. It will be of great use to us also.
Then one more point. One of the student or one of the participant, he asked about the different control strategy to know which method gives us more realistic result. So here, I mean, basically, in today's lecture, our more focus is on coordinating the electric vehicle charging and providing the adapted or aggregated charging power to different type of users. So that is more from the charging management point of view. But if we consider the controller point of view, considering the local distributed energy resources, then it is going to be another approach also. That another approach is going to depend whether we are connecting this distributed energy resources locally through AC microgrid architecture or DC microgrid architecture. And then based on, we need to define the functionalities, right? So I hope that this answer will help him in understanding his question basically. And then one student, one participant, he asked that operational cost optimization of fast charging station considering price uncertainty. Okay, so this is a NPU uncertainty also. This is a very interesting point, right? So of course, when we are charging the electric vehicles, right, then we need to develop some charging pricing mechanism also for a primary user, secondary user, or opportunistic users, and so on and so forth, and depending on the capacity also, right? And so this is a very good area, and based on that analysis, then to make the profitable charging station, considering the forecasted grid price and forecasted grid demand or constraints also, then to have more profitable, that charging station operator can develop their local distributed energy resources also for fulfilling the demand and making the more profit. So that is again a very good point also for further research work. Then one student, he asked that integration of photovoltaic and wind system into this one, right? So we didn't did the integration of the wind, but in one of the work, we did the integration of photovoltaic with energy storage for supplying the load of electric vehicle station, and that article is published in Taylor Francis part A. So if you are interested, you can refer that article also. And I believe that it is open access also. Then one student, he is asked that Norway is a cold country. What are the alternative renewables other than solar? So yeah, as you may be aware that yes, of course, Norway is quite cold and having the Nordic climate. So, but here more than, or let's say more than 95% of electrical energy is coming from the hydropower plant. So we can treat that it is as a renewables also. And that's good. Any other question? And then one more question is there, that is a dynamic stability will affect in case of weak grid for EV charging system. That is true. That's why we are working on developing the fast charging station and integration of distributed generators and managing the power locally in a coordinated way also. So that is again a very good point, because this exponential growth of the electric vehicles is of course going to impact on the power quality and the capacity of the distributed network. So it is really difficult to enhance the capacity of the distribution network. So here is a good opportunity for the distributed energy resources. In my opinion, in future, for example, solid oxide fuel cell or gas-fired generators locally will be used, right, for developing the fast charging station and improving the power system stability, control and operation, especially within the distributed network.
Good afternoon, sir.
Yes.
Good afternoon.
Hello.
Hello.
Hello. Good afternoon, sir. This is Neeti Dugaya from Oriental Institute of Science and Technology, Bhopal. It's really good to listen you again, sir. I just want to know whether you are, the impact assessment of electric vehicles on distribution system reliability is the topic in which I am working. So can you please, if you can please guide in this regard?
Yes, because one of my PhD student, she is basically based in Austria, but I'm the main supervisor, and she is working on impact of electric vehicle charging on the distributed network, considering the home charging, because at the home charging, right? So that is going to impact that is going to have as an additional load. And at the home, we may not be in a position to have the proper energy storage and like that. So this is going to impact the operation of distributed network, because we are going to have an additional load also. So this is a very good point, right? And I believe that in your research work, you may be considering all these points. For example, as we know that different electric vehicles or different type of chargers, level 1, level 2, those are going to be used basically at the home level. So the functionality or the characteristics of those charging units may be useful for doing distribution network analysis, especially with the power flow. And then of course you can consider that due to this additional load, voltage quality analysis also, and to improve the voltage, how we can have different type of reactive power compensation within the distributed network also. That is also another very important point also.
I can add one comment for that question.
Yeah.
So actually, with the rapid proliferation of electric vehicles within the fast charging station, we can see load variance. You can focus on load variance and the load factor in the distribution network, and also the thermal loading of the transformer and the transformer capacity violations. And then there is a serious issue with voltage drop. Okay, voltage drop, you can consider that also. Then there are some power quality issues also. It is another special area if you consider this power quality issues. That means the frequency regulation. If you consider the frequency regulation, it is a very wide area that you can do even a PhD, because you can incorporate many signal processing techniques to analyze how this frequency profile or the frequency profile has been distorted, and then you can very narrowly look at which places this frequency or the waveforms are distorted with different transforms, Fourier transforms, wavelet transforms, and like that, and deep learning practices, of course. Then you can propose innovative synthetic inertia techniques to mitigate these issues and like that. Because in the fast charging stations, we can see, because of this extra load, the distribution network has to be reinforced or reconstructed. That's why we always recommend to have a local energy supply. Okay, so basically the power quality issues and the voltage drop, if the charging process left uncoordinated, we will come up with voltage drop issue, and the load variance, transformer capacity violation. Those things happen in the distribution network. And for the student who has asked related with price optimization, I can suggest, I don't know your background, probably if you are a master, I think master's student.
PhD.
Huh?
PhD student.
PhD. Okay, so probably it is a very good start for you to work with the the simplest model. That is, you can consider you are going to purchase the power from the wholesale market, and then you sell your energy in the retail market. So based on that, and based on your, of course, your proposed strategies, you can develop your optimization problem with the relevant constraints. And or else you can think the same problem as a game theory. Yes, approach. Because I don't know, I don't have a clear understanding about your real problem. If you are trying to look at different fast charging stations, then, and if you are having some central aggregator, he will be the the main competitor or something like that. And then you can formulate, I have seen in literature, a game-based study with this what's called price optimization analysis.
Very good. So I hope that participants might have enjoyed or might have liked some of the highlights from the presented work. Yeah.
Hello.
Yes, please.
Yes, sir. Greetings to both of you. Sir, I am Devrat Rautray from Shiksha Anushandan University. Sir, my question is, you told that in CHAdeMO, that is a communication
from the manufacturer or the market, yeah.
Yes, sir. But Teslas are using also CAN. Sir, could you tell me the in between those two protocols, those two communication mediums, which one is the better one? I think Tesla.
I don't know, because both of them are commercially used, right? So there may be like there may be like some good advantages. That's why they have been used, right? So it's really difficult for me because I'm not working on the communication protocol at this moment. So really difficult for me to distinguish which one is good and which one is bad. But both of them are commercially used, right? So they may be good. I hope so.
But I think these protocols are compatible with the manufacturer, because the main purpose of this communication protocol is to you coordinate your charging side with the electric vehicle, because it should be synchronized with each other. So that is the main purpose of this communication protocol. Therefore, it is very difficult to distinguish which one is good and which one is bad, because I think it is compatible with all standards. But we don't have much knowledge in this. I'm not sir, but in my case, actually, I don't have much understanding about this physical layer functions and these communication protocols. So as per my knowledge, that's what we can suggest as a comment for you. Probably it may help your question.
Okay, thank you.
Okay, thank you, sir, for such an informative and educative session. I hope there are no more queries from the participants. Okay. On behalf of IEEE Power and Energy Society, Student Branch Chapter NIT Calicut, I would like to express my sincere thanks to our speakers who, in spite of their busy schedule, spend their valuable time for us by accepting our invitation to handle the session. Thank you, sir. Thank you very much for enlightening us by sharing your knowledge and experience. Thank you, sir.
Thank you.
Thank you.
Next, I would like to thank all the participants for your kind cooperation and support for making this event very successful. Once again, I thank all of you. Have a good day. Thank you. Thank you, sir.
Thank you, sir. Participants, please fill the feedback form and all. Thank you, sir. Thank you. Thank you, Sanagan. Thank you. Thanks a lot. Thanks for coming.
Thank you.
Thank you. Bye-bye.
Bye, sir.
Thank you, sir.
Bye,
Thank you
sir.
so much.
Bye, sir.
Okay, switched off the video.
Okay. I think it went off.
Yeah, it went. Do you see that?
Can you share the video recording? A request, can you share the video recording of this?
Shall I
Because we missed the initial
meeting will be closed for review.
Yeah, then we will see.
Can you share the video recording, sir? I'm audible to you?